From molten metal to glowing red rods, this is the story of how America's supergiant rod mill plants transform raw steel into the strength that builds our world. Each coil, each bar, each spark of molten light, forged with precision, power, and pride. Welcome to the incredible world of the supergiant rod mill plant. Steel. It's in our buildings, our cars, our power lines, even the bridges that connect our lives. But few ever see where it begins, in the heart of giant rod mill plants, where millions of tons of recycled scrap are melted, purified, and reshaped into the fine rods that power modern civilization. Before we dive in, don't forget to like, subscribe, and hit that bell icon, so you'll never miss our deep dive documentaries into the massive machines that make our modern world possible. It all begins with scrap metal. Old cars, demolished buildings, rusted beams. At the supergiant rod mill, these mountains of scrap become raw material once again. Trucks unload tons of steel at the scrapyard. Giant magnetic cranes lift and sort the metal by grade and purity. Anything that can be melted down and reused will be. Each day, tens of thousands of tons are fed into massive electric arc furnaces, or EAFs, the fiery heart of the modern American steel industry. Inside, electricity arcs across carbon electrodes, reaching temperatures above 3,000 degrees Fahrenheit. The scrap melts into a glowing river of liquid steel. Chemical engineers constantly test samples, adjusting the recipe with carbon, manganese, and silicon to achieve the exact properties needed for rod steel: strong, flexible, and consistent. When the chemistry is perfect, the molten steel is tapped from the furnace into giant ladles, each holding up to 150 tons of liquid metal, hot enough to light up the night sky. Next comes continuous casting, the process that turns liquid steel into solid form. The molten metal is poured into vertical molds and rapidly cooled by water sprays, forming long rectangular shapes called billets. Each billet weighs several tons and measures more than 30 feet long. Still glowing red, they're automatically cut and moved by mechanical arms onto cooling beds. From above, the plant looks like a river of fire, steel flowing from furnace to caster, from liquid to solid, from chaos to structure. These billets are the foundation of everything to come. In just a few minutes, liquid scrap has become a new form of strength, ready for the next transformation. Now the journey moves to the rod mill, the most precise and powerful section of the plant. Here, billets are reheated in gas-fired furnaces, soft enough to be shaped, but not melted. They're then fed into a series of rolling stands, giant pairs of steel rollers arranged in sequence. Each stand reduces the billet's thickness and elongates it, from a 150mm square bar to a rod barely thicker than a pencil. Over 20 stands, the steel races forward at incredible speeds, more than 300 feet per second, glowing orange as it twists and stretches through the mill. It's a dance of fire and precision. Every roll, every turn, perfectly timed. By the time it exits the final stand, what began as a massive billet has become a slender, flawless rod, ready to cool and coil. Fresh from the final rollers, the rod still glows red hot. It's immediately laid in spirals onto a cooling conveyor, a metal track stretching hundreds of feet. As air jets blow across it, the steel slowly cools, hardening to its final structure. Cooling too fast would make the steel brittle. Too slow, and it might lose its strength. Timing here is everything. Once cooled, robotic arms pick up the coils, each weighing more than 2 tons, and transfer them to the coiling station, The rods are wound into perfect circular bundles, tied, labeled, and ready for inspection. At the supergiant rod mill, precision is non-negotiable. Every coil is scanned, measured, and tested for diameter, tensile strength, and surface quality. In the lab, technicians cut samples and run them through machines that stretch, bend, and twist the steel to its limits. Spectrometers verify the chemical composition. Microscopes examine grain structure. Only coils that meet the strictest ASTM standards move forward. Every imperfection, even the width of a hair, is tracked back to its exact moment in production. Because when that steel becomes a bridge cable, a skyscraper column, or a high-speed train line, failure is not an option. Flatbed trucks and rail cars carry them to wire drawing plants, construction sites, and automotive factories. These rods become reinforcement bars, wire mesh, bolts, fencing, nails, and the fine steel cables that hold up America's bridges and skyscrapers. Each ton of rod steel is a link in the chain of infrastructure, invisible to most, but essential to all. If you enjoyed this journey inside the hidden world of heavy industry, don't forget to like, subscribe, and tap that bell icon, because next time, we'll explore another supergiant that powers our world. Water, the most abundant natural resource on Earth. But beyond drinking, irrigation, or transportation, it holds power. Immense power. In this episode, we take you inside the colossal world of hydroelectric energy, where millions of kilowatts are harvested each day from flowing water. From massive dams to precision turbines, from mountain reservoirs to electric grids powering cities, this is how hydroelectric power is made. Coming up, we'll dive deep into how gravity, water, and engineering come together to generate clean, renewable electricity at scale. Hydroelectric power, also known as hydropower, is the process of generating electricity using the energy of moving water. The principle is simple. Gravity pulls water downhill. That motion can turn turbines, just like wind spins a windmill. The key concept is potential energy. When water is stored at a high elevation, it has stored energy due to gravity. When it flows downward, this energy becomes kinetic, motion, which we can convert into electricity. The earliest versions of this idea powered water wheels in ancient civilizations. Today, it powers entire countries. At the heart of many hydroelectric systems is the dam. Built across a river, a dam creates a reservoir by holding back water and controlling its flow. One of the world's largest dams, the Three Gorges Dam in China, spans more than 2 kilometers across the Yangtze River. It can generate over 22,000 megawatts, enough to power millions of homes. The dam has multiple gates that control how much water is released. Behind it, the reservoir stores billions of gallons of water, like a giant battery waiting to be discharged. Engineers must carefully manage this water, especially during rainy seasons. Too much flow can flood communities downstream. Too little, and the turbines can't generate enough electricity. Once water is released, it travels down large pipes called penstocks. These pipes funnel water from the reservoir to the turbines below, often dropping hundreds of meters in elevation. The greater the height, the greater the pressure. This high-pressure water enters the powerhouse at incredible force, often exceeding 100 psi, pushing with massive energy. Some penstocks are as wide as subway tunnels and run several kilometers through mountainsides. They're made of reinforced steel to withstand the immense water pressure. At the bottom of the penstock lies the turbine, the workhorse of hydroelectricity. As water crashes into the turbine blades, it causes them to spin, just like a water wheel. These blades are part of a rotor, which is connected to a generator above. There are different types of turbines depending on water volume and head height. Francis turbines are the most common and highly efficient. Pelton turbines are used for high-head, low-flow systems. Kaplan turbines work well for low-head, high-flow rivers. Each turbine is massive. Some weigh over 100 tons and spin at hundreds of revolutions per minute. Every rotation turns mechanical energy into electrical energy through the generator. Attached to the spinning turbine is the generator, the part that actually produces electricity. Inside, magnets spin around coils of copper wire. This motion creates an electromagnetic field, which generates alternating current, AC electricity. The amount of electricity depends on how fast the turbine spins and how strong the magnetic field is. In large dams, each generator can produce hundreds of megawatts on its own. The electricity then travels through step-up transformers, which increase the voltage for efficient transmission across long distances. Once generated, the electricity is sent through high-voltage transmission lines from remote dam sites to towns, cities, and industries across the region. It passes through substations that reduce voltage to usable levels before reaching homes and businesses. Hydropower accounts for over 60% of all renewable electricity worldwide, making it the largest source of renewable energy on Earth. Countries like Norway, Canada, Brazil, and New Zealand rely heavily on hydro to power their national grids. Some hydroelectric facilities use a special system called pumped storage. It works like a rechargeable battery. During low demand periods, electricity is used to pump water uphill from a lower reservoir to a higher one. Later, when electricity demand peaks, the stored water is released back down to generate power again. This system is essential for balancing the grid, storing energy from wind or solar, and ensuring stability. Pumped storage plants can respond in seconds, making them ideal for backup and peak load times. Not all hydropower comes from giant dams. Small-scale hydro projects can power a single community or factory. Micro-hydro systems can power a remote cabin using a natural stream. These systems often have no reservoir, meaning minimal environmental impact. They're popular in mountainous and rural regions where rivers flow year-round. Installation costs are lower, and they offer sustainable power with little maintenance. While hydroelectricity is renewable and carbon-free, it's not impact-free. Large dams can flood ecosystems, displace communities, and block fish migration. That's why many new projects focus on fish ladders, sediment management, and run-of-the-river designs. Modern hydropower aims for eco-friendly integration, working with natural cycles instead of against them. Many older dams are also being retrofitted with fish-friendly turbines and smarter control systems. Balancing energy needs with environmental protection remains a challenge, but one that's being actively addressed. As the world shifts toward renewables, hydropower will continue to play a key role. New innovations like subsea turbines, gravitational storage, and digital grid integration are redefining what's possible. Floating solar panels on reservoirs are also being explored, combining two clean technologies in one location. Hydroelectric power isn't just about energy, it's about infrastructure, environment, and innovation. It powers our homes, our industries, and increasingly, our future. From the silent force of falling water to the roar of spinning turbines, hydroelectric power is one of humanity's most brilliant uses of nature's strength. Efficient, clean, and endlessly renewable, it's a pillar of global energy that continues to evolve. Thanks for watching. This is how millions of kilowatts of water energy are harvested and turned into light, heat, and life. Stay tuned for more incredible journeys inside the world of industrial innovation. Every year, billions of plastic bottles are discarded around the world, piling up in landfills, floating in oceans, and harming ecosystems. But what if we told you that these same bottles can be given a second life, not as more plastic, but as something entirely different? Today, we're taking you inside a modern recycling facility where innovation meets sustainability. From the moment a bottle hits the sorting line to the final bales of fluffy polyester fiber, this is the journey of how trash becomes treasure. Let's begin. The process begins long before the factory floor. Across cities and towns, used plastic bottles are collected from curbside bins, public recycling stations, and even from manual pickers scavenging landfills. Once gathered, the bottles are transported to a material recovery facility, MRF. Here they are unloaded in massive heaps, thousands of pounds at a time. The first step? Sorting. While PET bottles might look similar, not all plastics are created equal. Machines and human workers work together to separate PET, polyethylene terephthalate bottles, which are ideal for polyester production, from other plastics like HDPE or PVC. High-speed conveyor belts carry the waste under a battery of sensors. Infrared scanners detect the resin type. Optical sorters distinguish color. Air jets blast non-PET items off the line. Caps and labels, typically made from different materials, are also removed. Some facilities use label stripping rollers or even laser cutting machines to do the job with precision. Once sorted, clean PET bottles are ready to begin their transformation. Before anything else, the bottles must be thoroughly cleaned. Contaminants like food residue, glue, or dirt can severely affect the quality of the final fiber. The sorted PET bottles are conveyed into a granulator where rotating blades chop them into small flakes, roughly the size of corn kernels. These P flakes are then sent through a multi-stage washing system. 1. Cold wash removes loose dirt and residual liquids. 2. Hot caustic wash. A heated alkaline bath breaks down stubborn adhesives and sanitizes the plastic. 3. Friction washers. High-speed paddles scrub the flakes against each other to loosen contaminants. 4. Float sink tanks. Since PET sinks and other plastics float, this stage separates leftover caps or labels. Once washed, the flakes pass through centrifugal dryers that spin at high speed to remove surface moisture, followed by hot air dryers to lower humidity content below 1%. At this stage, the clean, dry flakes resemble plastic confetti, pure, uniform, and ready for the next phase. Now it's time to turn flakes into pellets, the feedstock for fiber production. Clean PET flakes are fed into a twin-screw extruder. Inside this machine, the flakes are heated to around 260 degrees Celsius, 500 degrees Fahrenheit, just above PET's melting point. Mixed and compressed through rotating screws, melted into a viscous, honey-like liquid. As the molten PET exits the extruder, it passes through a spinneret, a metal plate with tiny holes, to form thin strands. These strands are cooled in a water bath, then chopped into uniform pellets using rotary cutters. Each pellet is about 3 millimeters wide, compact, consistent, and easy to store. These recycled PET pellets, also called rPET, are now ready to be transformed into polyester fiber. In the fiber production unit, the rPET pellets are transferred into hopper-fed extruders, where they're reheated and melted once again. The molten PET is then forced through another spinneret, this time designed to form ultra-fine continuous filaments, each as thin as a human hair. As the filaments emerge, they are quenched with cold air to solidify, pulled at high speed to align molecular chains, increasing strength and durability, coated with an anti-static or finishing agent to improve texture. This process is known as melt spinning, and it's the same technique used for virgin polyester. But here, the source is 100% recycled. The filaments then pass through draw rolls, heated rollers that stretch them to the desired diameter. Depending on the end use, the fiber can be engineered to be soft and fluffy for stuffing or strong and coarse for textiles. The continuous filaments are then crimped, given a wave-like texture to improve loft and blending ability. Finally, the fiber is cooled and cut into staple length, short segments that resemble raw cotton. These are baled, weighed, and stacked, ready for spinning into yarn or direct use in filling materials. Quality is everything in recycled fiber production. Each batch of polyester fiber undergoes rigorous testing in on-site laboratories. Tensile strength checks for durability. Elongation tests measure stretchability.